Good afternoon, everyone, and thank you for your time to coming to my defense. I'm Yu Chen, and I've been working at Professor Xiaohu's lab for almost a year now. And today I'm going to talk about my thesis project on surface engineering of MOS2 nanosheets for tuning hydrodesulfurization performance. This meeting is scheduled for 1 hour, and I'll be talking about for 30 minutes. But feel free to interrupt me if you have any questions. We will be talking about my focus on hydrodesulfurization. Why are we doing this material? Doing the procedure of ligand engineering, and finally fixing iono support. First, I'll be talking about hydrodesulfurization, or HDS, which is an industrial process to remove sulfur contaminants from fuel feedstock to ultra-low sulfur diazole. As we know, sulfur oxide is a major emission of combusted fuel. In addition to health and environmental problems, sulfur in fuels can cause corrosion in pipelines by deactivating the catalysis. Therefore, it is important to note that to compare with those serious concerns, the sulfur emission have been regulated to historically lower levels. This figure shows major sulfur compounds in crude oil classified as either acidic or non-acidic sulfur. Acidic sulfur are reactive and easy to remove, while non-acidic sulfur compounds are stable and robust during HDS. In our study, we are using a model of silyl conversion as a model HDS reaction because they are abundant in crude oil. This reaction usually contains high temperature and pressure, so we need HDS reactor to reduce that harsh condition. Although noble metal catalysis such as platinum or palladium are active catalysis for HDS, they are always considered expensive and saccharide. And more importantly, sulfur will easily poison the noble metal catalysis used for the combustion. By contrast, transitional metal dicogonite or TMD materials are a promising material for HDS reaction because of their unique properties. They can selectively remove sulfur and stay stable under harsh condition of HDS. Moreover, they are relatively inexpensive and bulk compared to noble metal catalysis, and also has high activity during HDS. A type of TMD materials that are commonly used to HDS reactions is molybdenum disulfide, or MOS2. These materials, we could see that they have been using for almost a century from now, but the question is, how can we improve them better? Here is why we are interested in nanoscale of MOS2. I'm going to introduce MOS2 nanosheets. We are particularly interested in nanoscale because of size-activity relationship. In this figure, we could see bulk materials can be turned into nanoscale and to the extreme case of a single atom metal. We could see by decreasing the size of a material, surface free energy increase, and specific activity for catalytic purpose increase as well with support. Under this condition, MOS2 nanomaterials have the advantage of stably formed 2D nanolayers by a variety of synthesis methods, as well as have tunable properties for tailoring their applications. Another interesting property of this material is that their edge area are completely active for HDS, but the basal plane here is completely inert. Therefore, to maximize the edge area of this material per unit mass of catalysis, we hope we could achieve 4 nanometer size of materials to improve the activity. Synthesis of MOS2 can be classified as a top-down method and bottom-up approach. Typically, nanoscale materials made by top-down method has a disadvantage in no control in morphology or reparability. To overcome this, a solution is by a bottom-up approach, where a single atom of molybdenum starts by a smallest possible level at atomic scale and joined together with sulfur atoms to finally build up MOS2 nano layers. Various bottom-up approach have shown successful synthesis of MOS2. Here in our study, we are using a colloidal synthesis called two-pot hot injection method. In a typical process, oleic acid were injected into another hot solution of molybdenum chloride that contains ligands like olalamine. Then they were synthesized together at 180 degrees Celsius for 30 minutes to form a final product. Using this colloidal synthesis, we can achieve controllable small size of the nanoparticles that are 4 nanometers in size. This is ideal in terms of catalytic performance and surface free energy. However, a problem related to this colloidal synthesis is the presence of long organic ligands attached to the particle surface. As an example, oleic acid and olalamine can stabilize the nanoparticles in various nonpolar and hydrophilic media, as well as play an important part in self-assembly. But why are these ligands a problem? Because they could hinder catalytic reactions in hydrodesulfurization. As we run the sample in HDS reactor, we could see that nanoscale MOS2 conversion increased compared to the bulk. But for thousands of more surface area in a catalysis, this is not as effective as we expect them to be. This is because the bulky cap molecules on their surface creates an isolating barrier around each nanosheet and blocks access to molecular species trying to react with the surface. Therefore, it is important to modify surface of the nanosheets to improve their catalytic performance. Here we first did something called ligand engineering. An important step in ligand removal is to treat the nanoparticles with nitrocillium tetrafluoroborate or NOBI4. Here is the structure of this compound, and by applying this compound, they can replace original ligands and thus stabilizing the nanoparticles in various hydrophilic and polar solvent. The resulting solution was then washed with DMF, toluene, and hexene. To test our particles' ability to dissolve in hydrophilic media, we did solubility test and a stability test after every 4 and 24 hours. We could see in fresh MOS2 samples, nanoparticles disperse in the nonpolar cyclohexane. As by contrast, ligand-removed particles cannot dissolve in the nonpolar cyclohexane, but could dissolve in polar DMF. This confirms successful removal of original hydrophobic molecules replaced by a polar ligand. This nature is further confirmed by FTIR spectroscopy, In the blue curve shows before our removal process, and the purple curve shows after ligand removal. We can see that the peak at around 1300 shows the stretching vibration of CH group, and at around 3300 is assigned to amine group, that it is assigned to alanine ligands. We can see they are noticeably reduced after ligand removal, and that confirms successful removal of original oleic acid and alanine. Moreover, a new peak at around 1700 is the vibration of CO group, which is assigned to DMF molecules. This could also explain the high solubility and stability of the nanoparticles dispersion in DMF. Another thing we were concerned about is when we measure out our catalysis by mass, some of the mass might be moisture from air on the surface, or DMF, or NOBF4. We want to account for those weight, so we can always use the same amount of catalysis using in reactor run. Therefore, to measure out volatile components in our samples, we did TGA analysis. Subtracting the weight percent of water and DMF, we can see that the weight of just MOS2 catalysis is only 48%. But does this number make sense? Or are we having too much materials on here? Luckily, we could do math to confirm. So we first made assumption of geometry based on our TEM result shows on the left. We could see on average of 4 nanometers in size, and that equals to 30 units of molybdenum atoms across. Our second assumption is if we assume all Bi4 anion is attaching to one single sulfur atom, what's the expected weight of NOBF4? And by optimizing and considering the actual TGA result we observed, we could optimize the surface occupied by Bi4 anion was 41%. We then applied the same calculation to other geometry of MOS2 cantic, which are the extreme case of hexagonal and triangular. The expected result is based on assumption of fully occupied surface, and the actual result or the observed result is based on the TGA actual TGA we observed. We could see some key takeaways here is first, Bi4 anion is only partially occupying the surface, like the figure shows here. And second, this result makes sense, even compared with extreme case, considering repulsion of the ion group on the surface. But the point here is to show successful removal of original ligands and replaced by the anion group. XRD pattern shows similar curve before and after ligand removal, indicating our MOS2 nanosheets. We are still having MOS2 nanosheets. There are two things to note. First, the peak at 14 degrees showed in bulk MOS2 is the stacking layers of the nanomaterials. It does not show the same peak in nanoscale materials because there is no stacking layers. It is only one single layer of molybdenum disulfide. So so we don't see any sharp curve. And second, the thing here is to show the pink curve and the blue curve are similar. So sample did not change after ligand removal process. When we run our samples in reactor, the reactor result shows activity decrease after ligand removal. We think there are two reasons towards that. First, nanoparticles under harsh condition of HDS may not be stable because our HDS reactor runs at 300 degrees Celsius. So these particles tend to aggregate together without ligands. And the second reason is that our ligand-free samples dissolves now in polar solvent, and they tend to agglomerate and aggregate in the organic solvents of the reactor. So the question now becomes, if we can't change the solvent of the reactor, or we can change the harsh condition of HDS, can we prevent them from aggregating? There are ways we can do that, and that requires the use of a support. We want our particles to be dispersed and stick to the surface so that it doesn't agglomerate in ligand engineering. We hope to have nanoparticles that are stable, but the drawback is the loss of the surface area trying to attach to the support. The alumina is a promising candidate for supporting materials because it's low cost, high surface area, and high mechanical resistance. So the thing now left is how to integrate those nanomaterials onto the support. There are two methods we could do that. We first try to deposit the support by direct deposition method, but we see conversion of silophene goes down compared to just MOS2 and supported MOS2. We think this is because the pores of the alumina is only 3 nanometers, and they are too small for the nanoparticles to fit inside the pores. Therefore, we updated our method using incipient wetness impreg. In a typical process, alumina is wetted drop by drop with methanol and vanadium chloride to form orange catalytic precursor here and dried overnight. On the next day, we use the same hot injection method as we synthesis normal MOS2 nanomaterials before cleaning them with organic solvent and dried to get these dark particles. By this process, we hope to grow the nanomaterials directly onto the support of alumina to avoid aggregation in ligand engineering. This approach shows promising results when running them in the reactor. We could see comparable catalytic performance in supported MOS2 and just MOS2 nanosheets. We think this minor loss might due to diffusion effect because when we run our samples in support, some of the reactants might deposit inside the pores, and then extra paths may be required for them to diffuse out of the pores to finally convert into the product. And another reason might be due to the loss of some catalysis, because we did not know if it's actually 2% of catalysis inside the support. It is not a good comparison if we don't know what amount of catalysis we were using. But for time limit, we didn't do characteristic methods such as SCP to confirm that. But the point here is to show the use of catalysis to make the nanoparticles more stable, and the conversion might go down. But note here, we are using the batch reactor. A flow reactor are more commonly used in industry and may reduce the effect of diffusion. And I will get to that later in future direction part. And also note here, this is only a preliminary catalytic result, and we haven't determined the loading yet. So the conversion rate per unit mass might increase. In conclusion, in a typical treatment with NOBI4, we could observe successful ligand removal confirmed by FTIR and TGA. The result also shows BI4 anion partially occupying the surface. Ligand-free samples of MOS2 shows a low HDS performance without ligands, but with support fixing, we were able to achieve comparable conversions. So the next step we plan to do is, the first part is on support fixing, is on a characteristic method. We want to see how much MOS2 is in there, so we could do ICP to confirm, and also TEM and the XRD can be used to test whether it is actually supported. Second, we only focus on 2% of catalysis by now. So we also want to see other concentration of catalysis. And lastly, we could try, if we remove the ligands from the support, how it compare now to ligand-free samples and liganded materials. We believe there is still room to improve our catalysis by doping MOS2. Previous studies of cobalt-loaded MOS2 shows they are related to activating their basal plane. And zirconium vanadium doped MOS2 show related to phase retention during catalytic reuse. And finally, we could also try flow reactor that might reduce the diffusion effect and also more industrially relevant. With that, I would like to thank you for your time and acknowledge the wonderful people in our project, namely my professor Ayash Sahu and Steve for providing me valuable thoughts and guidelines. I would also like to thank current and alumni members in our group that kindly offers help there in lab. They supported me both emotionally and professionally that still remain my interest in this field. Thank you very much, and I would like to take any questions.